Why would someone disconnect?
I don't know, like, okay, so if I press it, it doesn't turn off, so then this should be the power. But then like, where's the car attached?
Where's this thing?
But no, like, this is, the car has power somewhere, like, where does it go? Oh, it's this. But where's that go?
That goes here, right?
Yeah.
That should be fine. There it is. Thanks. Don't need that.
Oh, a disconnect.
Yeah, so something's loose. What's loose? Is that?
It might be.
Where's that connected to?
This is
This
connected.
this is loose. I don't
But
know.
that's like
That's
another
a
thing.
speaker though, right? Yeah. What's this that's loose? Okay. Don't touch it. Because the guy's touching it. Okay, so that's a page. Hmm? 352.
Really should. Have sweat marks.
What's that? Yeah?
Yeah.
We'll go with page 352. Number 4. Okay, let's look at this. Okay, so read it over to yourself. Yeah, vertically upwards means out of the page.
But that's like just upwards. Does that mean like?
It's confusing. The reason why I translated it to mean that is because they mentioned that the alpha particle is traveling south. So if it's traveling south, what they mean is this. This is on the page. This is south. This is north. Okay, so that's west. That's east. So they're not going to say, if they meant north, they would have said north. So what they intended to say is out of the page. Okay, so that is my magnetic field. It is a vector. It has a direction. has an intensity. We have an alpha particle, which is positively charged. It's made up of 2 protons, 2 neutrons, traveling south. So the alpha particle is traveling this way. It'll hit the field. Remember, use a right-hand rule. It's a flat right-hand rule to determine the direction of the force acting on a moving charge. Either it's a current or a moving charge. It applies to either. It's all moving charges. If it's a current, it's a flow. It's a bunch of moving charges. If it's a single charge, as in this case here, same rule applies. Thumb is in the direction of that moving charge. Fingers, you can rotate about that thumb. It could be out, in, which direction did it say? It said it's vertically. Let's get the wording right. It says it's vertically, vertically upwards. They mean out of the page. So the fingers will point out of the page. The palm faces in the direction that the force is acting, to the left. On a positive charge, it would act to the left. So I'm just going to move it over. Well, if it's to the left, once it enters the field, it'll do this. It'll deflect in this direction in a circular path. It will continue to experience a constant force towards the center of this circular path, FB. Okay, there's a center. FB. FB. The force is always perpendicular to the velocity. That's how I know it's going to move in a circular path. So the velocity will be perpendicular. If this is, let's say this is the velocity here. Color it, recolor it in yellow. Velocity is there. It's tangent to the circle, perpendicular to the force at each point. I know the force, by its nature, by the nature of this magnetic force, always acts perpendicular to the velocity. So that's why it's going to move in a circular path and continue to move at constant speed. Okay, so that's the direction. Okay, so you could say direction is to the left or west, either one. Left of the page or west. F is equal to Q, V, B, perpendicular. It hits, let me just see here. Yeah, it's going to hit the field. The magnetic field is perpendicular to the velocity. Just by the very fact that this is headed south and the magnetic fields are pointed up, right? They're perpendicular to each other. I'd have to show you a side profile, so I don't want to spend too much time on that. So charge is twice that of a proton, 3.2. And the speed is 7.4. And the magnetic field is 5.5 Teslas. Okay, so that works out to be 1.3. Looks like it's 13. Okay, Newton. Don't, and again, make sure you mention the direction somewhere. It says calculate the magnitude and direction. That's why I mentioned both. If it just says calculate the force, it's the same thing. You need to include both. So calculate the magnetic force. If you see that as a question. That implies include magnitude and direction. Okay, so next we had to do 353. Five to eight. Yeah.
Can you explain again that FB like point on the field, the electric field, like in diagram that you drew earlier?
This one?
Yeah. Like the point, the white one, surrounded by the FB.
This point here?
Yeah.
That's the center of the circle in which it moves around. It moves in a circular path. How do I know? Because of the nature of a magnetic force, it's always perpendicular to the velocity. And that means that this velocity, whoa, it's not allowing me to draw it, but it means this speed will not change its magnitude. It'll move at a constant speed because the force is perpendicular to the velocity. It doesn't change the speed, it changes its direction, such that it's always pointed towards this center.
Is the center like a solid like thing, or is it just like P?
It's P, yeah. Yeah. If you were to allow it to move, had freedom to move in that circle, you could pinpoint where that center was.
Can the radius of the circle be however big like you want?
Yeah, we'll get into that later. It's related, obviously, to how fast it's traveling, how strong the force is.
Thank you.
Yeah. Number 5. Read that over. Calculate the magnitude direction of. Okay, so now we got to do this. We've got to calculate the field. So divide the force by QV. I'll do the calculation first and then. Force is 1.7. Proton charge is 1.6. Speed 1.9. Okay. This works out to be 5.6 Teslas. That's the unit for the magnetic field. Let's now figure out the direction. So the magnitude and direction. Okay. So I've got the magnitude. I need the direction. So if you had the question, simply calculate the magnetic field. If that was a question, again, include both magnitude and direction. A force is east. So a force is east. FB is east. proton is traveling north. That's direction of velocity. So finger in the direction that the positive charge is moving. Palm faces the direction that the force points. So you can rotate this. So the palm, in order for it to face to the right here, the fingers will point out. Fingers indicate the direction of the magnetic field. So the magnetic field is out of the page, indicated by dots. Dots are out of the page.
Oh,
There's this. Yeah. Very hot and
alright, I was right.
Okay, so I mean, you could just go over that again, right? Figure out that gives you the correct force. So velocity is upwards, thumbs upwards, fingers, if I'm right, out of the page, palm faces to the right as expected. Okay, next. 6. Read over 6 to yourself. Same equation. Give me a second. Talking about number 6?
Yeah, it says upwards force. Is it like vertically upwards or like this north?
Upwards force. Well, no, they would have said north if they meant north. So, well, upward they mean is out of the page.
But like in the other ones, they put like vertically upwards. But in this one,
Yeah, it's confusing, isn't it? So they meant vertically upwards. Yeah, out of the page. So, okay, let's do the calculation first. It's an electron, so the charge is 1.6. I know it's negative. I'm just calculating the magnitude.
this.
1.6 Teslas. Okay, now let's figure out the direction. An electron is traveling south. That's south. Okay, and it experiences an upwards force. They mean by that, they don't mean north. If they meant north, they would have said north. So upward means out of the page. Upwards force. So we're going to use red for the force. Experiences a force up. That's your force coming out of the page. Okay, so which direction is the field? Field has to be perpendicular to the velocity and the force. So you guys like using the left-hand rule. So because it's a negative charge, we'll switch to the left hand. Thumb points down, palm faces in the direction that the force is acting. Force is acting out of the page, palm should face out. Which way is the field? Yeah, left. So you draw the field like this. Pink is the field. Magnetic field is pink for us. You shampoo me that. Okay, whatever. There you go. Anyways. Double check. That. Yeah. Left-hand rule because it's a negative charge. Okay. 7, right? 7. I'm just gonna give you the answer. I think you guys can get that. I'll go into more detail with number 8. Just trying to save a little time here. So 7. Oh, interesting. Okay. So let's read it. It says the alpha particles traveling upwards at a speed through a magnetic field that's directed down. Interesting. Okay. Okay. So magnetic field is down. I didn't want to copy that. Anyways, magnetic field is down. And the alpha particle is traveling up. So the alpha particle okay. Down actually would be into the page, right? But I can't show that to you very easily. So I know it's a bit confusing, but I'm trying to show it to you from a profile you can see it. So the way they word it, I wish they didn't do it that way, but directed down would be into the page, and then the alpha particle would be traveling parallel to it up out of the page. But I'm just showing you a side profile so you can see what's happening. The alpha particle is traveling like that. Okay. So no force. Let's look at the formula. F is equal to QVB perpendicular. What this means, there has to be a part of the magnetic field that's perpendicular to the direction it's moving. If, as in this case, this is the velocity direction here. If the particle is traveling parallel to the field, there's no component of the magnetic field that's perpendicular to it. So no force is acting. So in other words, forget it. I wanted to, if I can lasso this. shoot. It doesn't help. It would have been perfect if I could just lasso this. Whatever. I'll redraw it. Okay. So if you had this, watch. As it is, it's parallel. No force is acting. But if somehow it was traveling like that, okay, let's expand it. It was traveling like that. Part of the magnetic field, part of this field here, this is your magnetic field here. It has two components. There's a component here and there's a component here. This component, that component there, is perpendicular to the velocity. And in that case, there would be a force. That's why when we do our problems in general, the particle moves like this, perpendicular to the field. And in that case, there is a force. There is a magnetic force in that case. Okay? It has to be at least part of the magnetic field perpendicular to the direction the charge is traveling for there to be a force. Okay, 8. Read that through. I'll draw a little diagram for 8.
So what is the force for number 7?
Pardon me?
So what would like number 7 be after that?
Because it's traveling parallel. There's no part of the magnetic field that's perpendicular to the direction it's traveling. So FB is 0. It's because this is 0. B perpendicular. There's no perpendicular part. Yeah. Okay. So this is actually just Bill, different equation, but actually related to the first one, QVB. So this is just plug it in. This would be a perpendicular 5 times 10 to the minus 1. Current is 3.6. And the length of the wire inside the field is 2.5. The answer is 4.5. Newtons. Okay. Okay. That's it. $296, that was working backwards. What was that? I had to do all of 296, so we'll backtrack to that. Backtrack to that. We're going to need this anyways, so might as well backtrack. Electrostatics. Hmm. Yeah, so read over number 9. Okay, so that's our conservation. Whenever we have a charge accelerated through a potential difference, we need to use a conservation law. And this right side is just replaced by QVBA. You're accelerating through a potential difference. This is just the old. I didn't put any subscript, but it's the old value. Okay, so it's just, again, divide top by bottom on both sides. So the charge and the negative sign will cancel out. Okay, so you just get the ratio of the new kinetic energy change over the old is equal to the new potential difference over the old. Let's just do a check so we're clear. It's accelerated through potential. So this, we've got the old, that's the first one mentioned. We also have the old kinetic energy. That's what's mentioned next. The question is, what's the new potential energy? Yeah, I'll do this. What's this? What's the new potential difference? Given the new energy. So we've got this as well. Let's just put in the numbers so we're clear. So the new energy, it increases from 3 to 9. I know it's 10 to the minus 17, but that's going to cancel out. So it's really this. It goes from 3 to 9. So the question is, what happens with the potential difference? The old potential difference is 4.2, 420. Okay, so the energy is 3 times greater. It goes from 3 to 9, 3 times greater. So this must be 3 times greater. So, yeah, so 840, it's about 1260. Yeah, 1260. Or 1.3 joules. Well, that's hard to see. Sorry about that. Okay. Number 10. It's got an initial speed. Interesting. It's an alpha particle, so it's going from the positive plates to the negative plates. It's attracted to it, so it's going to pick up speed. It starts, we'll call this A, B. So its VA is 7.15. $71,500. Yes, it'll pick up speed. The plates, we know the distance. We're given the distance. They are 9 times 10 to the minus 2 meters. We know the electric field. 1.7, 170 times 10 to the 2. What's the speed here? So what is VB? That's the question mark. So whenever you're passing through a set of parallel plates and therefore a potential difference, you need to use your conservation law, same as what we used above, same law. You're increasing your kinetic energy, whether you're increasing or decreasing. Whenever you pass through potential difference, you need to use, I'm going to skip the first step. You know it's change in potential energy, and that potential energy is given by QVBA. If we're accelerated within a potential difference, that's our potential energy, QVBA. Okay, now we don't have VBA, but we can figure it out. E is equal to VBA. It's related directly to it, divided by D. So just multiply ED. So this becomes on the bottom, negative Q ED, both of which we have. Kinetic energy, we can figure out what this final speed is. We have on the left 1/2 m VB squared. This is not zero. Remember, it starts with an initial speed this time. 71,500. Okay, mass, this is an alpha particle. So we have the mass of it. I told you to write it down. It's in your table. The mass is 6.65. Six 0.65 times 10 negative 27. Okay, same mass here. Charge, it's an alpha particle, twice the charge on a proton. It's 2 protons. 3.2. Electric field, we're given 170. D, we're given 9 times 10 to the minus 2 meters. So we have everything we need. Force this side. Here's the problem, the negative. It throws people. You know this side should be positive, right? You know it increases its speed because of the fact that it's moving towards a negative. It's got to accelerate. It's attracted to the negative. So the left side is positive. This side will be positive. Don't worry about the details. It's because this actually is negative, but that wouldn't come out in the math. You can only figure out the magnitude with this. So just force it the right side to be positive. Okay, the answer, your VB works out to be 8.11. 8.1. Yes, it's less than the speed of light, so that's fine. 11 is an electron. It's going to slow down. The trick with number 11 is you expect it to slow down because it's approaching a negative plate, which it's repelled by. Yeah, it does. Good. They tell you it goes from 5 to 1. What's the potential difference? Same equation. This one here. I'll rewrite it. I'll rewrite it in full. You have the VA, the VB, you have the mass of the electron. You can look that up. It's in your table. That's equal to negative QVBA. And you want to solve for this. That's the potential difference. You have the Q. Again, you have the mass. You have the initial and final A and B speeds. You can solve for it. This side is negative. So you force this side to be negative. Okay. Just 6.8 times 10 negative 1. So 0.68 volts. Okay, got to go on here. New topic, cathode ray tube. This is, what is a cathode ray tube? We still make use of them. You'll see them in scientific laboratories and that. This is what the old television sets were. They were big tubes that used magnetic and electric fields. This is a side profile. Okay, side profile. The cathode ray tube. What is it? It's basically, this is all glass. Huge tube. That's how the televisions look. If you look at the older television sets, you have flat screens now. The older television sets had a big back end because it was made up of this cathode ray tube. And what was going on was the following. What you would have, I want to make sure I'm consistent with yellow. Yellow is the movement of a charged particle. So what you would have at this end, I'm going to erase it because I've got to do it properly in a second here. But what you would have is an electron beam coming from here. The electron beam would start here on this end. It would travel through the inside here, and I'll go into detail about that later. You might want to erase this later. This is just a rough sketch. And it would be diverted to different portions of the screen. And it would trace out the image rapidly. And they still use them. We still use these things, but we don't use them as television sets anymore. We use them for screens and different laboratories and that. But this electron beam, it would be an intense electron beam that would change its direction due to a magnetic field or electric field. They use both. And it would trace up and down, up and down. It would actually trace an image out in rapid time. So fast that your eye wouldn't pick up on it, the fact that it was a sketch. Just a rapid sketch. And by the intensity, it could affect different pigmentation on the screen, and you would get color image. So this is an electron beam of electrons. I'm going to redraw it in a second. I've got to go into more detail, but okay, I'm going to erase this yellow beam. I'll come back to it. Okay, so this is a side profile. This area here, this region here is the screen. That's the screen, side profile of the screen. So if I were to twist it, if I were to face it towards you, it would look like this. Could be circular. They made them square. It could look like that. That's the screen. They just twisted it towards you. You'd be looking at the screen, and the electron would be sketching out an image really fast. Okay, so at the end here, where it starts, I'll start with that. The electrons would come off a charged plate, and they would accelerate through a potential difference. So these are plates. I'll put them actually in red. These are plates, charged plates. This would be negative, this would be positive. And the electrons created would come off of the negative plate. Make it a little bigger. It would come off the negative plate, and it would pass through. This is a positive plate here. Okay, so the electron that's the first part of this too. We've already done some of the physics already involving it. So the electron would pick up its speed according to the conservation law. It would increase its kinetic energy from 0 to some whatever speed is needed in order to accelerate it towards the screen here. I'm going to move towards that. Okay, now it's going to start from rest. So we're going to have, this would be our B plate. This would be our A plate. So we have mVB squared. There is no 1/2 mVA squared. VA is 0. So that's your first equation to be aware of. That's the electrons accelerating through the first set of plates to power it up, to get them to start moving. Once the electrons are moving, then they would have to be deflected. And there's two fields that are doing the deflecting. There's the magnetic field, which we've been studying, which they can switch the polarity on this. I'm just going to put north on top, south on the bottom. But they could switch the poles. They can operate these magnets electronically. So I need a little more room here. So the electrons would pass through the magnetic field, always runs from north to south. We could switch that direction and the intensity. We can make it as strong as we want. The stronger it is, the more the deflection. So, what the frick? Franco, can you close that door, please? What? Why? Stupid freaking program. Okay, I'll redraw it. So again, field runs from north to south. You could switch the direction. when needed. Electron is going to pass through these plates first. Electron's going this. Let's use the left-hand rule since you like that. Left-hand rule says electrons pass this way. We're trying to figure out which direction the force is. Which way is the force? Field points down. Force is the direction of the palm out. I think I'll draw that in pink since we're used to it. Let's just redo that pink. You guys like pink color from? That's the direction of the magnetic field. Pink indicates direction of the magnetic field. Which way is the force acting? The force, again, we just determined is out of the page. I'll do that in red. We indicate that by red dots. Okay. That's going to deflect. Okay, you can't see it from a side profile, but it'll deflect electrons. Just with this magnetic field, the electrons will pass up like this. This is a side profile. I looked at it from a viewer's point of view. This is the screen here from the side profile. This is a head-on view looking straight at the screen. You would see the electrons move. So we said out, so it would mean from this perspective, instead of, there was no magnetic field, that's what you'd see with a single electron beam hitting the screen. But this is with the magnetic field, divert it to the left. There'd be a force deflecting it. It would look like that, deflects it to the left. That's out of the page in the first diagram. Okay. Yeah. This is the problem when you draw it. You get kind of screwed up as far as directions. Okay, now let's see what happens when you add the electric field. Yeah? Oh, yeah. You can go. Let's see what happens when we add the electric field. So I'm going to just draw that in green here. So let's draw an electric field now. Cathode ray tube has both electric and magnetic fields. In order to do what? In order to deflect the beam, as in this case, magnetic field is deflecting it sideways. You can reverse the polarity so the stream of electrons could be deflected to the left instead of the right, back and forth, to make the trace. But to do a full trace, you have to go up and down as well. So the electric field does that. So let's draw in the electric field. So this would be, I'm just going to make sure I know. This would be a positive plate. This would be a negative plate here. Okay, I'm going to erase the stream here because now we can see from the side profile what the electric field does. The electric field is pointed away from the positive and towards the negative. Okay. This is a negative charge, however, that's moving. It's an electron. So let's say we turn the magnetic field off. It just passes straight through, and now it hits the electric field. Which direction is this electron going to be attracted, up or down? Yeah, towards the positive. So while it's in between these plates, it's hard to see because it's a narrow area. It'll be deflected up within that region. Once it leaves the plates, stops being deflected and just continues in a straight line. and hits a point above, this is the center, it'll hit a point above the center. Because it's attracted to the positive, it'll be deflected up. What would that look like from a head-on view? This is you looking at the TV screen. Instead of you seeing the beam hit the center, it's now going to be deflected above. So between the magnetic and the electric field, you could place that electron stream anywhere you want and trace out an image. Okay. Okay. Now, just a couple of things. We talked a little bit about this already. What happens when this electron, or again, you could talk about protons, any charged particle, enters a magnetic field. So let's redraw the magnetic field. We need to go more detail as far as what happens with the magnetic field. I have the magnetic field up here. I can redraw it. Yeah, perfect. Okay, I can't get rid of that last piece of white. Okay, so that's the magnetic field. We're zeroing in on it in general, okay? What does a charge do when it passes through a magnetic field? Well, we talked a little bit about that already. Let's add to this. I need more. Okay, magnetic field's acting down in this case. What does a charged particle do? What does the electron do? We can do it for electron or proton. Since we're dealing with the cathode ray tube. What does this electron do? Let me see here. Oh, I can't draw it properly. Okay, yeah, I'll do both drawings. That's fine. So, give me a sec. Electron moves in here. Once it moves into the field, it starts to experience a force. It has to have, in our cases, it's going to travel in perpendicular to the field, so that there's always a component of the field perpendicular to the velocity vector. In that case, a force is going to act. Force is indicated by red. So which direction is the force going to act? In this case, field's down in the direction of the fingers. Thumb is in the direction that the charge is moving. I'm using the left-hand rule because it's negative. Palm faces up. So this force is going to be up out of the page on it. So let's draw the field. Let's look at it from above. Let's see what that would look like. How would that appear? That's how we can see the path clearly. From above, the field is pointed into the page. I'm looking at the top. I'm looking from here, from that perspective, from on top. Okay, that's what you'd see. And then you'd see the electron entering. Say it's entering from here. Make sure I get it right. It's this way. It's entering here, keeps moving with that velocity until it hits the field. When it hits the field, it no longer moves in a straight line. It's going to start experiencing a force pulling it in this direction. Circular path. There's a force acting on it at each point. There's a force acting there, FB. That's the initial force that we drew. That's this one here. And then that'll change its direction. So there's a velocity here. There's a velocity here. Same speed. As the force is acting perpendicular to it, can't change its speed. All it can do is change its direction. It is a different velocity because of its direction change. Okay, I'm not going to do it, but it should be V1, V2, V3, different velocities. The force is always perpendicular to the velocity. That's a nature of this magnetic force, the property of it. And yes, if you had enough field, if I extended the field this way, it would move in a full circle. So the radius of this circle we'll call R, as we always do, right? Radius of circle is R. It's not a full circle, but it could, if we extended the field, it would move in a full circle. Okay. It is undergoing uniform circular motion. How do I know that? Because it's a property of the magnetic field that it's always perpendicular to the velocity, always acting perpendicular. Which means the speed will not change. That's what uniform means. The speed isn't changing. Okay. And since, again, the force is always perpendicular to the velocity, the force will always point towards the center of a circle. You can show that. So it is circular motion. So if it's circular motion, that means we can apply the following equations. FC is equal to MAC. FC in this case, what's causing it to move in this circle? It's a magnetic force. What's the acceleration? Well, you can write v squared over r, or 4 pi squared r over t squared. You can use either one, whatever's convenient. What about this? Can we get to more detail about the force and relate this force to the speed? Yes, that force is QVB. It's a perpendicular. In this case, it's easy. I told you from the beginning, the velocity is perpendicular to the field. Can we simplify this equation? Yeah, we can. Cancel out one of the b's. You get QB perpendicular is equal to MV over R. One of the v's cancels out. Okay, this is a helpful formula. You'll see this in the next section. So what does it relate? Any of these things. If you know what the magnetic field is and you know what the charge is and the radius of the circle, you can find the speed. That's a typical question. Charge mass ratio. That's a common question. What's the charge mass ratio? That's just this. I'll just rewrite it. Why do I need to rewrite it just last time? Charge mass ratio is this, Q over M. So you just rearrange it for Q over M. Q over M is equal to V B perpendicular R. That's the charge mass ratio. Now that's the equation you use when a charge travels through a magnetic field. It relates its speed to the magnetic field in the radius of the circle. Okay, so let's go over, try this out, page 360, 1 to 4. I'm glad I turned the light off. It'd be even hotter. It's too bloody hot. Yeah, well, it's air conditioned, right? So, isn't it? Or maybe it's not. Maybe we're just on the cooler side of the school. I've been assuming it is. You can open the windows. If it is air conditioning, it won't. I think it's just turned down air conditioning.
In the diagram.
Yeah.
For VBA, you wrote that it could be found by like E times D.
Yeah.
Can you just explain how that works?
For parallel plates,
Oh,
this is the equation.
okay.
And that I said in, you're talking about this set of problems that we did? Yeah, so parallel plates, the equation for electric field is potential difference over the distance between the plates. So I just rearranged. E times D is VBA. VBA is that. So I replaced VBA by E times D. That's all. Now the sign might not work out, but don't, again, just force it to be positive. Because you'll solve for it and get a positive VBA, but force it to be positive. Force this whole thing to be positive, which would make the VBA negative, but don't worry about that. Just force the right side to be positive. Okay, I'm gonna get some paperwork for you. Be right back. Got it copied, so. I always assumed it's air conditioning, like very slight, but I might be wrong. It just might be cooler side. Now you let me know if this cools it down, then I'm wrong. It's not. Hiding stuff.
Oh no. Like walk through like right now notes for it. Like really notes for it. Like,
Let me know.
like,
That helps. It does open the rest.
yeah, but
Distance to it.
What?
Yeah, it's just
Oh, is this like, distance is R? Electric potential. Potential energy.
It's going space use.
Is this something like this? Electric equals like R?
Circle for plates and use conservation. And connect potential. And potential you are spinning for the magnetic says.
Okay, whatever.
Today's Monday, right?
Yeah. Magnetic field that much. Or something perpendicular to the field. What's the radius of the arc of so there is one going like this, it's going upwards, and then now radius of the arc speed comes in and it's like arc that many meters. Magnetic field is so strong. Where's the velocity? What is speed perpendicular to r? Right, but then like what is like is this a vector of the force magnetism? Speed. I don't know, I guess you. Force magnetic. Is the force magnetic the same thing as centrifugal force? Nora, is the force magnetic the same as centrifugal force? Centripetal force? FB? Isn't that FM?
Like, then you should use it on like this example.
What is the speed of the particles? For example, you're trying to find the speed of the particles. And also, you can only have one. Oh yeah, you put that a left
And
one.
then
Okay, that makes
VR. Like going here. That you take the hit, you go to that one.
Like after they go into the magnetic field, do they just like stay there continuously spinning,
In theory, but like.
or do they just like keep going and then just like it's like what? Isn't that just like capture a bunch of them and then you just crowd a bunch of them spinning constantly?
No, that's just like some way you can think about it now. That's what like die or calculations.
See, I don't like electronics. Like electricity, it's too complicated.
Exactly.
Like mechanical, like you can see it work. Like yeah, physics is okay. Like
That's having
Okay. But then like physical objects I can observe. But this is just like really abstract. I don't like abstract things. I can't see them.
Wow.
That's why I like biology. Because me.
We have so many units.
Bone.
How many bones do you have?
Bunch.
Like,
52 at the most. Oh, a lot. That's like hundreds because they will.
wow, like, no. Funny bones.
We'll go over those questions in a minute. This is your relativity assignment.
Oh,
Read it.
I hate you, Galloway.
You hate y'all. Whoops.
Yeah, I created relative.
is
Read it. Make notes on it. 4 pages. No double space. That's it. That's due. We'll make that due. Well, we get back a holiday on Monday, back Tuesday, make it due. Got a test on Wednesday. I don't mind pushing it till Thursday, but no later, obviously. It's down days Friday, so due Thursday. 4 pages of notes.
Looks like,
Nice notes.
it wouldn't. It probably wouldn't hit right here. Like if they already moved, they would probably just like stop on the end.
yeah, but you dropped it like on the.
Due Thursday.
Right, so let's just say if this cart was moving, and I stand right here and I drop the thing, like right here, and it was moving, we'll probably just fall off the end of the cart.
I don't know
So it'll just stay
why.
stationary in
I got the exact amount, but I made.
Oh, does the hammer also make velocity? And then it's constants?
Oh, yeah.
Yeah. No.
You know? Like there's back.
Let's go over this. We'll take a break at 10. What's that? What are you saying? It's not on the exam. Relativity is not on the exam. Just do the assignment. 4 pages. Not double spaced, please. Okay, 1 to 4, page 360. We'll take a break at 10. Excuse me. And yes? Say it again. It's not on, no, I'm not examining you on that or testing you on it. What I'm testing you on Wednesday, for clarity, just so you know, is electricity and magnetism. So we're still covering magnetism. We'll be over most of it today. There's a little section I have to go over Tuesday. So, and I got to give you some handouts on it as well. I can, for practice, I'll do that during the break. I got time then. Okay. Yeah.
Centripetal force and the magnetic force, are they supposed to be like equal?
Yeah, in this case, the magnetic force is acting as a centripetal force.
I'll see.
Yeah, very good. An alpha particle travels through a magnetic field perpendicular to the field. The radius of the arc is 1.5. What's the speed of the particle? Well, it's traveling. This is it. That's the scenario. Where a charge, in this case, it's an alpha particle instead of an electron. But the effect is the same. The magnetic field acts perpendicular to the velocity and acts as a centripetal force. So I'll just derive it one more time, and then you've got to know it. It's a centripetal force. What's a centripetal force? In this case, it's a magnetic force that acts as a centripetal force. Okay, one of the V's cancels out. You're not given this equation, you have to derive it from what you're given. What's the speed of the particle? So solve for the speed, rearrange for that. Is that better? Are you finding the temperature better? Yeah, I'm not finished. I'm going to shut the door here. Yeah. QBR squared over M, yes. That's correct. Okay, same as above. This should be, oh, it's V squared over R. Jeez. I knew that. Just testing you. V squared over R squared, that's good. I invented a new formula. Okay. It happens. You're right. I'm wrong. Okay, happy? Good. QBR over M is equal to V. So what do we got? We got an alpha particle. Alpha particle is 3.2 times 10 to the negative 19. Magnetic field is 4.22. The radius is 1.5. It's an alpha particle, so we know what the mass is. The mass is 6.65. Yeah. (6.65) times 10 negative 27. Okay, and that works out to be 3.0 times 10 to the, I can't even read this, 10 to the 4. Were you off?
I got 3.1.
Join the club. Apparently I can't write squares and all that. Okay, that is the speed. That's all it's asking us for, just the speed. 2, person travels through a magnetic field, perpendicular field. We got the radius. What's the magnetic field? Same equation. Okay, just solve for the magnetic field. It's a perpendicular magnetic field. It's a proton. Mass of the proton is given to you in your data table, 1.67. Speed, 5.4. And then the charge, you can look up as well. It's called the elementary charge. I mean, it's 6, not 6.7. I know that. And the R is 7.2. 10 to the minus 3. Okay. So that works out to be 7.8. 10 to the negative 1 Teslas. Almost done here. 3. Calculate the charge to mass ratio. I did that for you. I derived it up here. right here. That's the equation for charge to mass ratio. You got the speed. They give you the speed. They give you the field. And they give you the radius. You got everything you need. Three. So it works out to be 8 times 10 to the 6. To the 6 coulombs per kilogram. Last one. Read that through. Okay, so in this, what they've done is they've set up the magnetic field so one cancels out the other. So what they're saying is this: the magnetic field creates a force that's equal to the electric force. They're equal. In that case, it would not deflect. That's what they mean. This is what they mean to say. The forces balance each other. So you have QVB. What's the electric force? It's just QE. There's no velocity in that. Okay. So just plug in your speed. And your magnetic field. And that works out to be 1.7 times 10 to the 5 newtons per coulomb. Yeah. Okay, so how did I know this is true? Just be clear on this. Because of the word undeflected. They're not deflected. And what they mean to say is, if you look at what it said earlier, it says the electric and magnetic fields are perpendicular to each other. So if you have the magnetic field this way, right, you have a charge running this way. Does that, now, let me redraw this. It's sometimes hard to get the directions right. See if I can do it as easily as possible for you. So the magnetic field, let's say, is into the page. Okay, yeah, do this. Magnetic field, let's say, is into the page. That's the magnetic field. Okay, and the charge is moving this way. It's a positive charge. Okay, normally it would be, if it was just a magnetic field, it would be deflected up. Like that. That's the way it would move. But it's not just a magnetic field. We're told that the electric field and magnetic field are perpendicular to each other. So I'll put the electric field in orange. So in order to deflect, in order to offset this proton from moving up, or alpha particle from moving up like that, in order to prevent that, we need a field that's acting down. We need a field that acts in this direction. Perpendicular to the magnetic field. That's the E field. What will that do? That will offset the magnetic force such that instead of the alpha particle moving up due to the magnetic force, the two forces balance. So there's an electric force now that's acting down on the alpha particle that's balancing the magnetic field that's acting up. Magnetic force, pardon me, that's acting up. They balance each other. Should draw it a little longer. Okay. They're now balanced such that this alpha particle ends up just going straight through. Undeflected. Straight through meaning it's not deflected due to the forces balancing each other. So FB will have to be equal to FE so that this takes place. It passes through undeflected. That's what I started with here. Okay, take a break.